The Nobel Prize in Physics for 2025 was just awarded to three incredible physicists, John Clarke, Michel Devoret, and John Martinis. What for? For something called macroscopic quantum mechanical tunneling. Okay, I know, that sounds like a mouthful of jargon, but stick with me, because what they discovered is genuinely it fundamentally changes how we see the universe and proves that the weird, bizarre rules of the quantum world don't just apply to tiny, invisible particles, they apply to things we can actually see. This is the story of how they proved that everything, no matter its size, is quantum. So, let's break it down. What on earth is quantum tunneling? Imagine you're rolling a marble up a hill. If you don't give it enough of a push, it will roll part of the way up and then roll back down, right? It can never magically appear on the other side of the hill without having enough energy to get over the top. That's how our everyday world works. But in the quantum world, things are different. An electron, for example, can be rolling towards that same hill. And even if it doesn't have enough energy, there's a small but real chance it will just disappear from one side and reappear on the other. It tunnels straight through the barrier. It's like a ghost walking through a wall. This isn't science fiction. It's a fundamental property of quantum mechanics, and it happens all the time at the atomic scale. For decades, physicists thought this weirdness was confined to that tiny, subatomic realm. We see it with electrons and wires, but surely a bigger object, something made of billions and billions of atoms, would behave normally, right? It would follow the classical rules of physics that we see every day. The big question was, is there a line? A point where things stop being quantum and start being classical? Is it about size, or is it something else? This is one of the deepest mysteries in physics, often illustrated by the famous thought experiment, Schrödinger's cat. This is where our Nobel laureates come in. They wanted to build an object, a system, that was big enough to be considered macroscopic, but that would still behave like a quantum particle. They needed to see if a big thing could also tunnel through a barrier. They used something called a Josephson junction. Now don't let the name scare you. A Josephson junction is basically two superconducting materials separated by a very, very thin insulating layer. Superconductors are materials where electricity can flow with zero resistance, and the electrons pair up into something called Cooper pairs. Think of this Josephson junction as our quantum particle, but instead of its position, we're interested in its phase, which you can think of as a point on a circle, like the hand on a clock, just like a marble in a bowl. This phase likes to sit at the bottom where its energy is lowest. We can create a hill or a barrier by applying a tiny microwave pulse. According to classical physics, if the phase doesn't have enough energy to get over that barrier, it should stay put. It's stuck. But if quantum mechanics still applies to this relatively large system, then the phase should be able to tunnel through the barrier even without enough energy. And that's exactly what they set out to measure. John Clarke and his team in the 1980s were the pioneers. They built these circuits and cooled them down to near absolute zero to minimize any thermal noise. They applied a carefully controlled microwave pulse, not strong enough to kick the system over the barrier classically, but just enough to see if it would tunnel. And they saw it. They observed that the system could escape its energy well, and the rate at which it escaped matched the predictions for quantum tunneling perfectly. This was the first evidence of macroscopic quantum tunneling. But there was a catch. How could they be absolutely sure this was quantum tunneling and not just good old-fashioned thermal energy? Even at near absolute zero, there's still some residual heat. Maybe that tiny bit of heat was just enough to randomly kick the system over the barrier, making it look like tunneling when it wasn't. This is a crucial point. To prove it's quantum, you have to prove it's not classical. This is where the work of Michel Devoret and John Martinis became so brilliant. They refined the experiment in a groundbreaking way. One of the key predictions of quantum theory is that if you excite a quantum system with energy, it can only absorb that energy in discrete packets, or quanta. It's like a staircase. You can be on step 1, step 2, or step 3, but you can never be on step 2.5. A classical system, however, is like a ramp. It can absorb any amount of energy smoothly. So, they zapped their Josephson junction with microwaves of a specific frequency. What they found was astonishing. The system would only tunnel when the microwave frequency exactly matched the energy difference between the quantized energy levels inside the well. If they changed the frequency even slightly, the tunneling rate dropped dramatically. This was the smoking gun. A classical system, being kicked over by heat, wouldn't care about the specific frequency of the microwaves, but a quantum system would. This spectroscopic evidence proved, beyond a shadow of a doubt, that they were witnessing a purely quantum phenomenon on a macroscopic scale. What does this all mean? It means there is no dividing line. The weird rules of quantum mechanics don't just disappear when things get bigger. The universe is quantum through and through. The only reason we do see our coffee mugs tunneling through the table is because for an object that large, the probability is so astronomically small that we'd have to wait longer than the age of the universe to see it happen even once. but the possibility is there. The discovery by Clarke, Devoret, and Martinis didn't just solve a deep philosophical question about the nature of reality. It also laid the practical groundwork for the entire field of quantum computing. The qubits in today's most advanced quantum computers are essentially the direct descendants of these experiments. They are macroscopic object circuits on a chip that are deliberately controlled to be in quantum states of superposition and entanglement. So, when you hear about Schrödinger's cat, you can now say that, in a way, physicists have built it not with a real cat, but with a superconducting circuit. They proved that this macroscopic cat can be in a superposition of states, and that it can tunnel through impossible barriers. They showed us that the quantum world is in some strange, separate realm. It's our world. We're all living in it. The work of these 3 Nobel laureates opened our eyes to that fact. And in doing so, they not only deepened our understanding of the cosmos, but also launched a technological revolution. Thanks for watching. If you enjoyed this deep dive into the quantum world, don't forget to like, subscribe, and hit that bell so you don't miss our next video. See you next time.